moment generating function. Moment generating function. So what are they? So it generates my moment. So let me get a formal definition. What? So this simplifies computation. Whatever I told you, I'll just write that. By providing compact way to derive. By providing compact way to derive any moment of a random variable, RV, random variable, through differentiation. Differentiation is easier. So what does it do? This provides us alternative. Okay, this provides an alternative to PDF, whatever provides alternative to PDF or CDF way to find the moments that we were discussing earlier, right? We integrated all this. You saw for uniform and this thing, right? We integrated and found this. Instead of doing this whole steps, this makes our life easier. It provides some alternative to PDF or CDF. So let's continue. What is it? What's the intuition? So the nth moment, okay, or let me give you the formula. So the formula, this is the main formula. So moment of any variable, random variable x, is given by expectation of e to the power tx. Okay, this is the MGF. This is the moment generating function. This is MGF, and this is the expectation of e to the power tx, and x is the random variable. This is the main formula, and let's see what is the main magic behind this. So we know that, so we know the exponential formula, right? What is e to the power x? This is equal to 1 plus x by 1 factorial plus x square by 2 factorial plus x cube by 3 factorial plus so on till infinity. This is about e to the power x. What is our moment generating function? This says that this is e to the power tx. So replace x with tx. So what will this become? E to the power tx is equal to 1 plus tx by 1 factorial plus tx. Now let me write it open. T square x square by 2 factorial plus t cube x cube by 3 factorial plus so on. And there will be tn xn by n factorial plus it continues. Okay. Since what is my moment generating function? That is given by mxt's expectation of t to the power x. Now, what is the beauty? So this is equal to, okay. So now this is the formula e to the power tx. Now, what will be the expectation of e to the power tx? What will be the expectation of this? Wherever x is there, we replace this with that corresponding expectation. T is a constant with respect to x. So that will remain as it is. As I mentioned, the expectation of a constant is the constant itself that comes outside. X is the random variable. So let's put those values. So this will become 1 plus t times expectation of x by 1 factorial plus t square times expectation of x square by 2 factorial plus t cube times expectation of x cube by 3 factorial plus so on. And here I'll write one more term. Say for example tn expectation of x to the power n by n factorial. This is expectation of t to the power x. This is nothing but our mxt. This is our mx of t This is our MGF, moment generating function. Now do you see, this is what is this what is this? This is my mean. This is my first moment, x square, second moment, x cube, third moment, x power 4, fourth moment. So whatever we are talking about these moments, right? These are the raw moments that we are talking about. There are other kinds of moments also, central moment, standardized moment, etc. There are more moments, but this is what we are talking about, the central moments. No, sorry, the moment, raw moments. Okay, so don't worry about those, but understand this. So e to the power, that single power, first power of x is mean, second power is variance, third power is skewness and all. So each of these terms are my moments. Okay, let's write it down that way. So this is equal to 1 plus, if I put t, this is my first moment, m1 by 1 factorial plus t times m2 by 2 t square times plus t cube times m3 by 3 factorial plus so on, t to the power n by nth moment by n factorial plus so on. This goes on. Okay, this is my mx of t. This is coming from here. Okay, so till so far so good. We know that, sorry, that how this is linked to the moment. This how this expectation, the moment is defined like this, e to the expectation of e to the power tx. We know what is the e to the power tx. We expanded that, and then wherever x was there, that became our moment. That corresponding power became that moment. Okay, moment, first moment, second moment, third moment. And now if we do, okay, let me write it down here, where mn is equal to nth moment. And now if you want to find this moment, what was in the definition? Using differentiation. This is important. This is important. So we use differentiation. So this is your nth moment. So if we differentiate mxt with respect to t, first derivative, okay, so this is generally, this is m dash x t, this is equal to d by dt of mx of t. So what will this give? This is the equation of mx of t. So this one is constant, this becomes 0. This t will hold, this t derivative will become 1, and this m1 will be as it is. So this will give me 0 plus m1. This t square will give me like something of derivation 2t m second moment by 2 factorial plus so on, and there will be more terms, higher terms of t. So I have differentiated for the first time, one time. This is my first derivative, m dash x, and this gives me the, if you see here, this is the first moment remains. Rest of the terms are having t. This I have got this. Now, okay, now set t equal to 0. As soon as we set t equal to 0, all these terms having t, they will become 0 now. What remains? Everything after this will become 0, 0, 0, because every term has a t, t square, t cube, t to the power n. Everything will become 0. What remains is m1. So this will give me that m dash x of t is equal to m1, first moment. Similarly, if we have the nth moment, okay, similarly we can say that m double dash x of t will give me m2, because again this has no t term. This will become constant. This is 0, this is 0. These two terms go, and this t will also go, because dt by d, this will 2 will remain. Only m2 will hold, and rest of the terms will have t in them. And we set t equal to 0, so these are gone. So my second moment will remain. So this is my m2, and so on. You can just keep on going. Okay. So this means, if we generalize, expectation of x to the power n. What is nth moment? Okay. So just this is equal to, this is nth moment. So this will be expectation of x to the power n. This is nothing but d by dt of nth time mx of t. Do this and then set t equal to 0. You will get the expectation n. I hope this is clear. Then if I have to write variance, how will I write now? So for example, if I write variance of x, how will I write this? Can we write it as m dash of x at 0? I'm putting t equal to 0 directly. This was t, right? This was t equal to 0 minus m dash of x 0 whole square. Second moment, first moment whole square. This is expectation of x. This is my expectation of x, and this is my expectation of x square. So now using this, we can calculate using the moments, we can calculate the variance directly, and this is what makes it so computationally easy. I hope moment is clear. Moment generating function is clear. It's simple. Just take the nth derivative and set t equal to 0. And the formula here is given by expectation of t to the power x e to the power tx. Okay. And just a note that not all the random variables may not have moment generating functions, because maybe the integration of the PDF does not converge. It tends to infinity. So in that case, we will not have a moment generating function. So I'll just write a note for that. Okay. Let me write. Not all probability distributions have a MGF, moment generating function. Since integrals of PDF or CDF, whatever, PDF may not the PDF only may not converge, and that may tend to infinity. Okay, for example, if I remember correctly, Cauchy distribution, okay, there it may not converge and it will become infinity, so we will not have a moment generating function. Okay, so now we can use this if we know the moment generating function. That is the first note. And second note is, if we know the moment generating function then of a random variable, then no need to do integration. Okay, separately, no need to do integration. So this is what it is important about MGF. This makes our computation easy, and this is what is used for computation. That's why moment generating functions are important.